Good afternoon, everybody. At the outset, let me welcome you to the second day of this online course on advances in remote sensing technology for geological applications. So, this lecture is dedicated to understanding of remote sensing applications in engineering geology, recent advances. So, let us begin with what we understand about engineering geology. It's a science which deals with the engineering properties of rocks. So, here we do not call the rock as such. In geology, we generally delineate different rocks, but in engineering geology, we most frequently we call it rock mass. So, what is the difference between rock and rock mass? We have to start this lecture with this difference. So, rock mass essentially has to contain weak planes, or maybe it is a joint plane, maybe it is a fault plane, or unconformities. So, any sort of weak planes that bound the rock by volume, that will be called the rock mass. So, rock mass when it is put in a particular environment, that basically gives us the engineering geological situation. So, that is how the engineering geology as such as a subject has evolved. So, what are the range of tasks if you need to understand that is involved in this particular study? It involves pure geology, it involves soil and mechanics, rock mechanics specifically, it involves a little bit of civil engineering, lithology or rock types, structure, engineering characteristics, and suitability for a particular engineering project. So, whatever we are doing after studying this course, studying this particular lecture, suppose engineering geology, we suppose we are going to implant a kind of hydroelectric project or a roadway project or something like that, an infrastructure development project. So, to come up with such a project, what are the prerequisites? So, basically basic prerequisites basically has to take cues from these disciplines called pure geology, soil rock mechanics, civil engineering, lithology, structure, and engineering characteristics. In this lecture, we will cater to all the engineering characteristics, and obviously we will touch upon all other aspects as well. So, to start with, let me show you this aerial photograph. What I why did I put it at the beginning is that I want to make the students understand that what at all are involved in this study. If you get a satellite image or if you get a aerial photograph like this, apparently what are the things you can get and what are the things that becomes important, particularly in terms of engineering geological realm. So, this photograph basically represents an interbedded dipping sedimentary strata. So, sedimentary rocks are involved there, and where you see they are dipping towards a particular direction. So, this particular structure we call a flat iron. Iron is simply iron for pressing. So, that is how the aerial view or the planar view of an iron will be like this, a triangular facet, and most importantly, to determine the direction of dip of these beds or the topography, you have to look at this, search for this apex, and the direction that is tapering, the flat iron is tapering, dip is just opposite to that. So, here all beds are dipping this way, just opposite to the tapered end. So, this photograph gives you an overview of what are the rocks that is exposed. You can see some rocks with brighter tones, you can see some dark tone rocks and different textures, different patterns, different associations. So, taking everything, all the image elements we call it, all the image elements together, we can discern different type of lithologies. In this particular case, there is a alternation between sandstone and shale. Sandstones generally they are hard compact, so that is why they appear as a resistant cap like rock or a hill like rock. On the contrary, shales will get very easily eroded. So, over the time they create a depression. So, that is why a depression and a hill and depression, this continuously we get in this photograph. And due to their properties, chemical properties, due to their grain size, all these basically gives rise to different types of tone, texture, different types of drainages, right. So, that is what is generally kept before you as an satellite or aerial photograph. Now, what all things you can get it from, what all things you can derive from this photograph? Can you see a general trend of the bedding? Bedding means simply where the lamination is dipping. So, a particular trend of bedding? Can we search for that? From this image we can see that what are the basic strike lines, general strike lines of the beds present in this region. What is the basic dip direction? Is there any fault or fold axis or archimedes? What are the joint sets present? So with examples later on we will try to get informations from satellite images, or we call it earth observation parameters. We will try to get these informations from. So next we need to understand, I started with rock mass, the definition of rock mass. Now if I am clear about what a rock mass is basically volume of rock bound by different joint planes or planes of other planes of weakness. So now how do I classify the competency of the rocks? In general geology we may have acquired knowledge on different types of rock, their structures, etc. But in engineering geology we need to know specifically what is the competence of the, how strong the rocks are. So if I have to build something upon the rock, then we must know what is the how strong, how competent the rock is. So from what I can get to know about this? So from there are 7 points jotted down here. Please look at first we have to consider the uniaxial compressive strength, we call it UCS, then RQD, rock quality designation, then weathering characteristic, joint other fractures spacing, fracture openings, continuity and filling, orientation of the fractures and groundwater condition. From these 7-8 parameters we can get to know how strong a rock is, and whether the rock mass is homogeneous or no, whether there are alternations coming or whether there is a uniform pattern, uniform spacing. So that is how, taken all these together, if we classify the rocks, if we can classify the rocks at all, the classification basically gives rise to different classes, and suppose 5 classes in general sense, and so that ranges from very good to very poor rock. And these 5 classes, suppose I give maximum 100%, 100 to the most competent one, very good rock, the upper limit of the very good, and 0 for the very poorest of the poor rock. So in between we can make suppose 5 divisions with an interval, equal interval of 20-20. So these groups basically gives rise to 5 classes, and we have to get certain numbers, we have to assign certain numbers to these rocks. Suppose I am calculating all these 8 criteria, considering all this, I have in a way that I can call a rock that it should get 49 marks. So 49 marks that comes between your 40 to 60, this group. So group 3 or class 3 we may call it. Similarly, a rock which belongs to class 5 rock is most competent. Most competent means that it can stand by its own without any outside support. So and if you have sufficient, if you have a structure that is supposedly to be built upon that rock, particular rock, it can sustain that load of the structure or no. So that's what. Now to continue with this discussion, we need to understand that what are the properties, index properties of rock. What I have described in the previous slide is a broad classification, broad aspects that we need to consider. But what exactly as index properties of different types of rocks we have to get information from. So first is porosity, then there will be density, permeability. But forget about that. Most important in this class is the strength parameter of the rock. So what strength parameters are there? There are 3 strength parameters. There are 3 stresses. If we know, if there is a compressive stress, so if I put a normal stress upon a surface, or so that is basically compressive or normal stress, and suppose I pull it apart, so a fracture in between develops, so that is basically a tensile strength, and there is a shearing, so one plane shear past each other, so that basically gives rise to shear failure. So accordingly we have 3 different stresses, so normal stress, tensile stress and shear stress. The rock from within basically fights against these stresses. Nobody wants to fail. So if the rock has to fail, its competency has to be superseded by the applied forces. The forces are basically compressive stresses, tensile stresses or shear stresses. So if any of these stresses wins against the strength of the material, so then a failure happens and the rock develops some kind of fracture or something like that, or a faulting happened, or a landslide happens. There are several manifestations. So for each of these stress parameter, we have corresponding strength parameters in the rock. So to measure, to understand the competency of the rocks, then we need to understand what is the compressive strength of the rock, the tensile strength of the rock, and the shear strength of the rock. Again, please understand, strength means from within the rock is basically fighting against the outside forces and it's trying to sustain itself, and beyond a particular yield limit the failure happens. So if the competence is more, if the strength is more, the competence of the rock will be more, competent. Anyway, so compressive strength is basically if you are putting a normal force like this and then at what load it fails. Then tensile strength, if you are putting a tensile stress like this, at what after what strength of the rock, then a failure happens. Or suppose a shear strength, you are putting a shear stress along the boundary, between the contacts of these surfaces, and at after a particular limit there is a shear failure happens. So that strength, shear strength, becomes important to us. So we have to understand at what limit that failure has happened, at what limit this applied shear stress has superseded the shear strength parameter. So that basically is the yield point or the critical point. It should not be superseded, it should not be passed by my shear stresses, applied shear stresses. So if the shear stresses is too much and it supersedes the shear strength, then shear failure will happen, and a typical signature in nature is a landslide will happen in this case. Right. So as for the landslides, because if we have to study about engineering geology, I will touch upon very basics of landslides in this lecture, and tomorrow I have another lecture where we will have detail about geological disaster, and specifically on we'll spend substantial amount of time on landslides. So today I am going to give a basic idea about what landslides are. So obviously landslide is a broad term, so it's a umbrella term, and within that ambit we can have all these classes. So each of these diagram, please understand, they are basically one type of landslide. So this axis is my material involved. So this is rock, this is your debris, and this is earth. Earth means nothing but soil, and this is where the process involved. It can be fall, it can be topple, it can be slide, spread, flow, or complex. So accordingly I have rock fall, debris topple, or suppose earth slide, like that. So it generally happens this way. So there are these 16-17 classes that happens under the broad categories of landslide. There is a graph that I call it the physics of landslide. So this is basically a tug of war between the normal stress and the shear stresses, and if the shear stress is too much, if the normal stress is too much, then it compels the shear stress to go beyond the shear strength limit, and the landslide happens. This is called the Moore-Coulomb failure criteria, and this we are going to understand in detail tomorrow, not today. What we need to understand today is the rainfall relations. Rainfall is a typical feature, suppose, and specifically for landslides this particular trigger is very important. We need to understand why rainfall is important. There has been a lot of discussion going on around the globe that rainfall is a causative factor or a triggering factor for landslide occurrence. It may appear that rainfall quite often triggers, so there is a heavy torrential rainfall and then the landslide starts happening. So that way that is a trigger, but if you understand it deeply, then we know that there has to be some role for rainfall as a causative factor. If the rainfall doesn't happen, suppose deep monsoon or late monsoon, we have landslides, but landslides immediate before the landslide we have slight amount of rainfall, not that much, but then also the landslide happens. It's only because the slope has been kept ready. Slope is basically saturated, it's matured in terms of landslide occurrence by the antecedent rainfall. So mid of the rainfall season or end of the rainfall monsoon season, we have landslides because of this reason, because the slope has been kept ready. It is to maximum extent it has been saturated, and with this saturation level now I need a slight trigger. If the slight trigger is there present, then the landslide happens. So that's how we need to understand from this graph. This is where the landslide in real terms has happened, and this is how the rainfall goes up. This is typically cumulative rain in millimeter. So and this axis is time. So rainfall monsoon continues, rainfall goes like this, and there is a sharp rise. So monsoon peaks basically in the sharp rise in the rainfall, and that basically continues up to this spot where at this time the landslide happens. Please understand, this steep slope of the rainfall is important. So this is what we call as a trigger of the trigger for the landslide. But what about this? So engineering geology, if we need to understand the role of antecedent rainfall in landslide occurrence, is very important to acknowledge the role of this factor. So if the antecedent rainfall had not been of this value, then this point should have been somewhere here. And if this point, the critical intensity starts from this point itself, then it can never reach this point. So that's how I have to get this antecedent rainfall, this slope, and this value is something, it may appear trivial, but it is perhaps not. It's very important, because this much of rainfall only, that is the antecedent rainfall, that suppose it's happening there for last 15 days, last 20 days, last 1 month. So this is the total rainfall, and then if last 1 month it had rained like this, then only the slope can start from this until it reaches the landslide occurrence point. So that's how it's not the only critical duration is important, along with that antecedent days of rainfall are also important. So there are different threshold models for landslide initiation. So there is a particular type of landslide, particular amount of landslide in terms of millimeter, in terms of total amount, or in terms of duration happens, and then only we have seen the landslide to occur. So threshold is the minimum rainfall, minimum duration, or minimum amount of rainfall beyond which there will be a trigger of landslide. So there are different models, some are empirical, some are physical based models. So they basically help in getting the threshold, but believe me, it's a very easy task. And how we do it, let me explain. So there are different thresholds. So T1 is for a particular river basin in a particular area. Suppose in one monsoon we have seen that one landslide happened in a particular area. So that is T1. T1 is basically threshold of occurrence of one landslide, minimum one landslide to happen in that area. T2 is 2 or more landslides to happen in that area. T3 is the threshold for 3 to 5 landslides to happen. T6 is the 6 to 9 landslide. T10 is more than 10 landslides. Obviously, if more than 10 landslides happen in that area, that means rainfall also has to be that much of extent. So T10 obviously demands more rainfall intensity, more rainfall duration. Now, how do I calculate this? We take cues from R3 and R5. R stands for the cumulative rainfall. So cumulative rainfall 3 days and cumulative rainfall 15 days, including the day of landslide. So today is 12th March. So including today 12th, 11th and 10th. So from 10th, suppose we calculate, we consider the total rainfall, cumulative rainfall, that will be my R3. So 10th, 11th and 12th. And similarly, R15 is the total cumulative rainfall for last 15 days, including the day of rainfall. Now, if I plot this R15 by R3, so R15 and R3 are what? Basically, they are cumulative rainfalls measured in millimeter. So, if they are plotted in a diagram, XY plot like this, what you see here, and so each of these points basically has a 15-day rainfall value and a corresponding 3-day rainfall value. But what does this indicate? This basically indicates number of landslides that happen. Please understand, there are this this green triangle is for one event. This one purple block is for 2 events. Blue triangle 3 to 5 events. So 3 to 5 events whenever happened, it happened with how much 15-day and how much 3-day cumulative rainfall. So that is plotted here. And if we plot that, please understand, I got my blue line here. That simply indicates this is the threshold. So this will be the T3. This simply indicates that beyond this, towards this side, there will be no blue triangle, but up this side there will be all my blue triangle. So that simply means this is a threshold. So beyond this, there will be no 3 to 5 landslide incidents happening. So it simply means that this is where, if the rainfall, if your suppose the landslide has not happened and you do it, you want to do this analysis in a predictive way, whether 5 landslides will happen in a particular area, no. So you, from initial rainfall, from previous rainfall data, monsoon data, you get this T3, and suppose next year on a particular event you have R3, and on a particular date you have R3 and R15 value, you plot it, and it's plotted somewhere here. So beyond this line, so that means we are in safe. But if it is plotted somewhere this side, beyond the blue line this way, so that indicates that we can have a landslide, 3 to 5 landslides very soon in that area, if not already happened. Similarly, we have this green line standing for T1 equation. T1 generally, the minimum 1 landslide to happen generally is not considered, because that is too trivial to take, because 1 landslide in a particular area in a particular monsoon season can happen due to many reasons. It can be simply due to your road cross cutting and other anthropogenic factors. So that should not be considered. We have to start from T3 at least, then T5, T10 like that. So obviously T10 demands more R3 and R10. So that's why all my points are plotted this side. So it demands more R3, more cumulative 3 days rainfall and more cumulative 15 days rainfall. So this is the beauty of rainfall threshold. This is a very nice way to present my rainfall data and get some idea about how thresholds work. But mind it, till now what we have discussed is all only about the amount of rainfall in millimeter. But what about the duration of rainfall? So this much of, suppose 50 mm rainfall happened in last 2 hours, 50 mm rainfall happened in last 4 hours, or happened in last 8 hours. So all these will have different impacts of on landslide occurrence. So that's how my duration and intensity both are important. So intensity is basically millimeter per hour, and this way is my time again. So if I plot, so these are from different this Nandprayag, Kanprayag, different areas, and we have got landslide. How many landslides happen in the Nandprayag area? So we got this many dots. So that means in Nandprayag these many landslides happen. In Pipalkoti these many landslides, all yellow dots are happening. So for that whole, all these locations are from coming from Alaknanda River Valley here in Uttarakhand. Now, for the whole river basin, we can jot down all my landslide points and we can draw a threshold. So beyond this, there is no dots. So that simply means my minimum rainfall has to be of this much value, this much of intensity, then only a single landslide event happens. So this other way of projecting your rainfall data. So previously we were dealing only with the amount of rainfall. Here we have the intensity of the rainfall. So both are equally important. Right. So let us come back to the properties of material, and we will start with the mechanical properties of the material. So suppose soil we have. And for soil, it is very important the size and shape of the particles and the relative density of the consistency of the soil. There are two types of major soil. One is cohesionless, like your that deals with the relative density, and cohesive soil. So it has to be consistent. So that simply means cohesive soils. Cohesion is the force in the binding force that keeps the soil particles together. And simply on a layman's term, if you touch a soil, if it feels sticky on your hand, so that is cohesive. And cohesionless, how do I make you understand? Suppose you go to beach and you take a sand, handful of sand and allow that to flow. So fall again, it will flow just like that very easily. So that's cohesionless. Cohesive soil is something that sticks to your hand. So that's how. So the cohesion simply is the force that keeps the particles together. So obviously they are important because they do not allow the clay particles to move apart from each other. This basically leads to the coherence of the clay particles, and it indicates that they are not going to be failed, at least shear failure wise, they are not going to be simply shear failure is failed very easily if it is cohesive soil. But if it is cohesionless soil, then there will be failure happening. So, Atterberg limits, next we need to understand these terms. So, Atterberg limits is simply when if we have a suppose we have a clay lump or we have a ground rich in clay, and then on that we want to construct a factory. So, infrastructural building we want to construct on that. So, that factory basically has to sit on the clay, and that is how the clay we have to understand what type of clay it is and its Atterberg limits. By the term Atterberg limit, we simply mean that if the clay is changing its state from liquid to plastic to semi-solid to solid, then in how much duration it is happening. So, why it is important? Because suppose clay is clay is saturated, and then it happens in monsoon. So, next the monsoon passes away, then next summer season it comes and it is dried up, heated, so the water escapes, and next monsoon again water comes in saturated. So, there will be a change in state of the clay. So, how well the clay basement basically can accommodate this change becomes a crucial factor for the stability of my building. So, if the clay basically changes from liquid to plastic limit very easily, or plastic to semi-solid, or semi-solid to solid very easily, that means in between limits we call it liquid limit, we call it plastic limit, and the shrinkage limit it happens in a frequent manner. So, in 5 minutes of time, 5 minutes of heating, we reach the liquid limit, another 5 minutes we reach the plastic, another 5 minutes we reach the shrinkage limit. So, that simply means the soil can get swelled up, or it can easily be dried up. So, that is basically dangerous for any infrastructural building that is going to come up on that is going to be constructed onto that. So, that is why we have to be very carefully, we have to very keenly see that in how much duration my limits are happening. So, if I heat the soil up and then the moisture escapes, so basically initially we have the decrease in volume, and after the solid limit is reached, then there will be no change in volume. So, before that there will be constriction in the volume, and then after that the volume remains constant. So, why they are important? Because they are important to know beforehand, before construction of before building a structure on that soil, and so what type of soil and how it behaves with moisture, that is very important to know. So, we have plasticity indices there, and depending upon where the plastic limit is located, we can get whether it is a non-plastic soil, low plastic, medium plastic, or highly plastic soil. Next application related to remote sensing for engineering geology. We very often construct important infrastructural facilities like dams, etc. on river barrage or river basins. So, the dam is basically a concrete structure, and once that is built, it at the back of that, at the upstream side, it creates a pondage, a reservoir created. So, first of all, if I have to construct a dam kind of thing, if I have to build a dam on a river basin, we have to look at where the river is the narrowest most. So, we have to look for the bottleneck where the river is narrow. The narrow river basically gets me advantage. We have to deploy less amount of cement. The cost basically becomes less. So, first point is the bottleneck of the river basin. Second point is how strong my abutments, the side walls and the basement are. Third is suppose it is for electricity generation, then I have to make sufficient water available in the reservoir, so that whenever I want, the turbine can be rotated with using the water, and we get the electricity. So, for that, essential prerequisite is that the reservoir should have sufficient water. So, we have to build our dam in a particular location where the water availability is there. So, if I construct the dam in a location where there is a major tributary coming, it is making a confluence with the main stream. So just downstream of that, if I make a if I construct my dam, so the water will be made available from the main stream as well as from the tributary. So the catchment is basically added up. So we have catchment from the main stream, we have the catchment from the tributary as well. So that basically makes sure that sufficient water is always available. Now, from remote sensing, what are the things that we can see? How satellite image can help finding this criteria, suitable locations. So first, we have to see the lithologies, the type of rock, what type of rocks are there. Our satellite image can, whether it is, if it is not vegetation is not there, so different types of rock types we can get to know, and wherever we see suitable rock types, competent rocks are present in situ, we can go for the construction of the dams. Then water drainage pattern, how the drainage is happening, subsurface, surface structures and environmental impacts. So some major processing techniques, I mean where from we get cues, where we have to put the most suitable alternate site locations. Which are the locations? From how a satellite image can help? It can help by getting you a geological mapping, it can help you water drainage. From DEM, basically it digital elevation model, so we can get to know how big is the catchment, how much water is available. Or the structural mapping basically helps where that basically helps you to know where a fault runs and where the major joints are there, or if there is a shear plane happening. So if all these are there, then there is a possibility, especially if it is present in the reservoir area, it's very dangerous, that it basically open gates for leakage or seepage happen all throughout the life of the dam, and the reservoir with time will have substantial amount of seepage, so that water storage becomes a problem for that. Then finally the dam site selection. So there are different algorithms are there by which, keeping all things together, we can select alternate dams. Mind you, it's not only construction of dam. If it is for especially for electricity generation, along with dam site selection, we have to construct, we have to look for sites that is suitable for powerhouses. I have to get locations for the tunnels. We call it HRT and TRT, headrest tunnel and tailrest tunnel. So headrest tunnel basically is employed to draw water from the reservoir and bring it to the powerhouse. Then the turbine is rotated, and again the water from the powerhouse is released back to the river. So that is called tailrest tunnel. So headrest tunnel and tailrest. Quite often it happens that this headrest tunnel and tailrest tunnel, they have to be subsurface. If they are subsurface, then at what depth they are happening, if that is possible, what type of rocks the tunnel has to go through, has to encounter, whether they are competent enough or no, or they collapses by itself. So those are very important. Last but not least, we have to get analysis called environmental impact assessment, or EIA. That is basically, once a dam is built, what are the effects that it will happen at the dam site and at the downstream. So how far the natural pristine serene environment, suppose, was happening before the construction of the dam is maintained, and if the dam is destroyed, suppose, what will be the impact of flood at the downstream, like that. Right. So as we know that the lithology was, you have to get the location, origin and extent of the bedrock outcrop. Then structure wise, we can start with 1:20,000 scale mapping, and so that is at the reservoir scale. Or if we have to go at the dam site exactly, we may end up in 1:5,000 scale. That detailed scale mapping is also required, because then because you are constructing a dam, concrete structure upon a basement, and if it doesn't sit on a competent rock, there is a heavy chance that it may topple after some time, maybe due to the load of the water, maybe due to the recurrence of the seismicity in that area. So anything, you do not know. So the following photolineament elements are important for stereographic study. Suppose you start with a stereographic photographs. What you see the shape, the cross section, the length, azimuth, frequency, density, and what are the relationships between the lineaments. Why lineaments are important? Lineaments are important because they are the linear structures and they quite often indicate the underlying weak zones, because any lineament or a linear structure present on the surface is basically plane in 3D. So that plane, how big is that plane, what is the extent, how dangerous is the plane, whether it is open, it is filled with something or no. So there are major lineament types: morphological lineament, then there are tonal types, there are vegetal types, so different vegetation type, pattern on texture, land use type, all these can act as different type of lineaments. Please see, you can see a particular type of change in color here. So that is basically, this is basically the ridge of this Shivalik hills. So this side there is a different type of vegetation, this side there is a different type of vegetation. The drainage also is different. Please see, there is a drainage like this, and after that the drainage becomes coarse. It's a fine drainage here and the drainage becomes coarse. So what is happening here, it is basically due to the change in lithology. So here it's more dominated in sandstone type of rock. Here it is muddy or clay type of rock. So that's why the drainage is fine, and here the drainage is coarser. So if you do not have an idea about what type of lithology is there, but if you look at the drainage, you can get substantial idea about what could be the rocks present there. Right. So we have been telling about the lineaments. So these are the major lineaments. Most of them are geomorphological lineaments, or some are structural lineaments. There are some structural faults as well from the Doon Valley only. This is your Shivalik Hills, this is your Lesser Himalayan Hills, and there stands your Dehradun city. So there are different fans are present there. So this part, basically sand colored, is basically your older Doon gravel and younger Doon gravel, and this is basically my Lesser Himalaya Nagthad quartzite and Chandpur phyllite it starts with. So quartzitic phyllitic rock. So this is my Shivalik Hills. Shivalik Hills is mostly sandstone silt clay conglomerate, and this is where my Indo-Gangetic plain starts. So if you come from Delhi to Dehradun, so you have to cross like Indo-Gangetic plain, then you have to go to the Mohand Hills or Shivalik Hills, then you land up here in the Dehradun fan. And if you want to go to Mussoorie, then from this fan you are progressing towards the Mussoorie. As you gain height, you are getting onto the quartzitic and phyllitic rocks of Lesser Himalaya. So geological structure, to continue with, please understand how a fault or completely joint controlled surface topography looks like. This will look like something like this. There are different crisscrossing of the joint sets, and you can look at the fault. So this line was continuing here, then it has it's not continuing. There is a curved like line like this is continuing, or suppose this line, and this is the fault line, and this way it is absent. So it's because the repetition omission of the beds has happened. By this you can get to know that how strong the phenomenon has been, so that on surface today we get only the lineaments, but if you are constructing a dam somewhere here, suppose, so it's very close to these lineaments. Lineaments may act as zone of weakness anytime in terms of seismicity, if you or in terms of, suppose if you create a reservoir there, they can act as your probable avenues for leakage or seepage of water. So that's how they are important. I was talking about the joint sets. Please see how many joint sets are present there. There are at least 3 sets of joints are present. This is a metamorphic hard rock terrain and highly jointed. So highly jointed rocks. Please see how it looks like, and there is a crisscross. So these joints are important. They happen to be the zones of weakness, but at the time when the environment is arid, when suppose I am searching for exploration of I'm onto exploration of groundwater, it's a arid dry region, and then ground wells are drying up. So these are the locations, engineering geology wise, these are the locations where there is a crisscross of joints. So different joints coming and cutting each other. So these are the locations are important. The qualities of the joints are basically the base site where you can look for the groundwater in this kind of metamorphic igneous or metamorphic rock regime. So please look at the sites where there is a cross cut of the joints. So general sense of understanding is that when there is a cross cut of different joint sets, so the different zones of weakness are matching, are coalescing. So they basically act as places where it can store some amount of water. So if you drill your rig there, or if you drill your hole there, well there, you may supposedly get some water. How a lineament is created on the surface. So lineament, so I have shown you that how it looks like lines on the surface. But suppose there is a dike kind of thing happening there. There is different two types of rocks, and there is a dike like this in 3D. And on that dike there happens to be surface, there is no manifestation, only except a particular type of vegetation is present. And if this vegetation is present, and this vegetation is not there anywhere, there is no elevation difference, no rock type difference, nothing, plain quaternary sand, but there is a particular vegetation, naturally it happens to be like this, continuing in this fashion. So that simply indicates there has to be a structural control, subsurface control, which basically guides the vegetation to grow in this fashion, because the vegetation gets nutrients from that dike. So suppose the dike is a dolerite dike or basalt dike, so it's getting its required nutrients from that basalt horizon only. Side by side it doesn't have those nutrients, because the rock is not present. So but here it's getting the required nutrients, and that's why they are allowed to grow. They continue to grow in this linear fashion. If this kind of feature, naturally occurring vegetation, happens to be in this linear feature, there must be some structural or lithological control. From the groundwater perspective, if we look at, we have to understand that there are different zones present. Some are surface water bodies like this. It's black because all my reflectances are getting absorbed in satellite image, in false color composite suppose, and there are some runoff zones where I know that the runoff, if the rain falls, the runoff will happen, some residual hills. Then there are some conduits for groundwater movement. So these conduits are basically this paleo channel or old channel, and it matches this, it coincides with, not coincides, it intersects with this lineament or joint, and that basically then becomes the conduit, the avenues for groundwater movement. So it can be a fracture, can be a lineament. Then there are some barriers of groundwater movement. So please look at this. These are these red lines. They are basically on surface. Why they are red? If it's a standard false color composite, they basically indicate some kind of vegetation. That's why the red. My infrared information is infrared reflectance information is putting in my red gun. So that's why in this false color composite they are appearing as a red line. So this red line, apparently because it contains surface vegetation, so there must have been some groundwater also, is related to groundwater only. So that's why this simply indicates that groundwater zone should be close along this lineament, and it's getting averted suppose against these black lines. The black lines are dikes. So dikes are so there's a dolerite rock or it's basalt type rock. They basically, wherever present, they become a kind of impervious rock which blocks the avenues, the flow of the groundwater, surface or subsurface, and that's how they are blocked. By saying this, apparently it means that they are blocking the, so there is a normal passage of groundwater doesn't happen. So but at the same time it's not bad, because if blockade is happening due to a dike, then the storage happens on the other side. So if the storage continues to happen, it may create a zone of potential groundwater horizon where future earlier it was dry suppose, now in future aspects future time these are the locations where we can get groundwater from. Another application in remote sensing for engineering geology is tied up with the construction materials. You know what construction material is? Suppose we are constructing something, a dam kind of thing, or a powerhouse, or a road network. Then if a dam has to be constructed, some material is to be blasted, and along with concrete, some material is to be put. So what material along the concrete, cement is to be put? Why to bring it from far off places? Along the river bed, whatever is available, the cobble, boulders, so take them along and bind it together with the concrete. So the material that is available over there only, that is readily being consumed as construction material. So as because they are basically getting used is in the construction material. Sometimes the blasted up material can be reused, or sometimes you have to mine it from the riverbed and use it as a construction material. So that's how they are important. But how remote sensing is important? Remote sensing, basically from satellite images you can get to know where the construction materials or the boulders are lying and in how much volume, what is the quality. So that locations of these construction material at the DPR stage, detailed project report stage of the dam, suppose, is to be obtained, and they have to tell that the authority has to tell that the construction materials available there will be collected and will be, thus it will be reused in the construction of the dam. This photograph, this aerial sorry, this satellite image simply indicates different type of rocks. At this stage, why I am putting this, I have jotted down almost all applications of what can be done from remote sensing for engineering geological studies. We started with the landslides, then we on to lineaments, then different type of rocks, different structures, different lineaments, dams, construction material. Now slightly detail about the lithology part, because this first thing that you look, if it is not vegetation is not present there, first thing that will appear to you is different rock type. So here this patch, whiter patch, is granitic rock. Generally granitic is acidic type of rock where quartz and feldspar, porous feldspar are present, so that gives you this type of tone and this type of structure. Then there will be dolerite dikes, this linear feature, black color. So basalt has to be black in color because it's pyroxene and plagioclase feldspar. Then there will be quartzite. So there is a difference between granite and quartzite. Quartzite is slightly grayish, it may be appearing, it's again brighter tones only. Then there are limestone. This typical yellowish or greenish pattern what you are getting here is a limestone feature. Then there is a shale. If you remember the first terrestrial image what we have seen, there is alternation between shale and sandstone. So same thing is happening here. This brownish color, slightly darker, that is basically shale. And then the quartzite. So this quartzite is alternating here again. These are the locations where the groundwater irrigated area. So these are the locations where they are occurring. Which locations they are occurring? They are occurring toward the quartzite and the shale and the limestone. So obviously they are cavernous, so they have some kind of heavy broad joint sets, so that they allow the groundwaters to pass, and that's how they remain to be irrigated. This water can be used for local cultivation, etc. So first point was the identification and mapping of prospecting groundwater zones. In this way we can get to know where the prospective groundwater zones are there. Then site selection of artificial research structures is very important, where the nature is not recharging the locations, but there is a high demand. So what we have to do, we have to artificially recharge those. And if there is a structure, by here by the term structure I mean that it's bound by some impervious membranes or some dikes or something, fault, something like that, so that there is already a bed so which can hold the water, hold the groundwater. If it can hold the groundwater, then if you recharge it, the water remains there. If you by some means, if you can draw the water that is available in the monsoon onto this bed, and as because it is underground, so you can reuse that in winters or in summers where there is a need of water. So that's how this selection of the artificial groundwater, artificial recharge zones. But where that will happen, you have to look for a suitable area. So in your engineering geology, your knowledge about the joint sets, faults, lithology, structure basically helps there to identify these. The identification and mapping of groundwater irrigated areas, as we have seen, groundwater resource assessment, how much water is available, and then upscaling. If the aquifer is already present, suppose, then if upscaling can be done, it can be broadened, it can be widened. By how it can be widened if there is a serious need, the aquifer itself is to be upscaled. So that those answers also we can get from the engineering geological analysis. This is broad geomorphology. For broad geomorphology, I have attached this photograph. I couldn't resist myself to attach this photograph perhaps. So this is the Indo-Gangetic plain, as I have already explained. These are Shivalik ranges, and there lies your Himalayas, the lesser Himalayas. In between, this yellow line perhaps indicates my main boundary fault or main boundary thrust, and this is your Himalayan faultal thrust or HFT. So there are two thrust zones. In between these two, we have the dune city standing there, located there. So that stands on a fan. So this is called my dune fan. Similarly, right and left we have Donga and we have Bhogpur fans. So major river is coming from that, and that river mound material is basically giving rise to this kind of fans. So they are mainly cobble, pebble or bouldery material along with sands. So these fans are locations where groundwater can be stored. So that's how they are important. We know where the surface runoff will happen and where the groundwater as such can be stored. Please mind it, this lies in between the Jamuna. This is the Jamuna river. This is the Jamuna Tier fault. There's a fault happening here. This point, or supposedly it has to be somewhere here. So this is the Tier fault. So the river Jamuna comes like this, and this side comes your river Ganga, river Ganges. So in between river Ganges and river Yamuna, we have these three fans at least, sandwiched between the Sivaliks and the lesser Himalayan hills. Now this geomorphological map can be helpful for understanding in terms of engineering geological competence of the rocks. So here it is mainly your dune gravels type of materials. So gravelly materials, how strong they are, they are not compacted, but here this mainly sandstone conglomerate type of rock, and this is lesser Himalayans. So that means they are phyllite and quartzite. They are quite competent, quite strong rocks. Next to that is this, and this is completely unconsolidated, uncompacted material. We'll end this discussion with the last analysis, last example that I have taken cues from seismicity. So how engineering geology and the seismicity or the earthquakes can be related. What all can be done from remote sensing in GIS studies. We can do seismic microgeneration. So seismic microgeneration like this of Dehradun city. This is a ward-wise city of Dehradun, and it basically gives the seismic microgeneration. What it basically tells, it tells you the velocity of the shear wave. Shear wave velocity, it basically has predicted, and with that we can zone different areas, and from that we can get to know where the chances of more damage is happening, and within this zone what are the buildings that is happening there is competent enough, or a retrofitting has to be done in terms of making it in a smart city. Then next comes the liquefaction modeling. Liquefaction is a phenomenon where there is on the surface, suppose there are three prerequisites. You have to have sand on the surface, you have to have subsurface shallow water, and there will be seismicity coming in. So earthquake happens, so sand and water is there. So what happens is that there is a movement due to seismicity, and for small period of time, few seconds, what happens, the sand goes down and water comes up, and the buildings which were earlier standing on sand now stands on water, so they topple. So that is the effect of liquefaction. Then for neotectonics and the crustal deformation, we know that the Indian plate is moving towards the Eurasian plate is going down, and then by due to this phenomena, Indian plate is slightly moving in an anti-clockwise direction with a particular millimeter per year value, where the movement is maximum, and how they are helpful in understanding the neotectonics part. Next is seismicity induced landslide hazard assessment. This we will do in detail in next tomorrow's lecture, but as of now we understand that seismicity along with rainfall, I have introduced you with the rainfall triggered landslide, but seismicity also can trigger landslides, and what best we can do in terms of hazard zonation when earthquake strikes. There is no rainfall, but still the seismic movements are there, and that's why landslide happens. And there will be the co-seismic deformation that is very easily can be detected using differential SAR technology, microwave technology, and especially slow moving landslides, or there is a landslip, or there is subsurface deformation, so landslide, so the land is subsiding. All these features can be well caught. I end with one example. That's what exactly I was discussing about liquefaction. So this is your normal condition before earthquake. Your groundwater is onto this level, but after earthquake, please see the capillary is bringing the water up to this. That means the water is, all my pore spaces are now filled with water. Earlier these pore spaces were filled with air in this place. Now they are filled with water. So that indicates that my buildings which were earlier standing on sand now stands on water. So that's how they will topple. So exercise that we did in Bhuj earthquake 2001, long back, that happened in the 26th January of 2021 on morning of 51st Republic Day of India. And what we have got to know is that, please look at this photograph very carefully, is the Run of Kutch. I hope you understand Run of Kutch. And then one of this side 2, suppose if I zoom it, so 26th is where the landslide happens, where the earthquake happens. 23rd January, you see all these, your salt plains or land is there. Now 26th January, on the day of earthquake, please see a river appearing on the surface. So river appears on the surface. It continues to stay up to 29th. So please see, the river is still there. River was not earlier, but because of the liquefaction event, the subsurface water, as because sand is available there, subsurface water has drawn itself up onto the surface, and the damage has happened due to that only. Again, on 4th February, after a week almost, the river is again vanished, is gone back. So this kind of analysis, we have not done it in post facto way, but for dangerous areas where this kind of liquefaction event is quite prominent, apparently we can do a priori analysis and let people know. We can create or keep our maps ready where there is a chance of the shallow subsurface water during the seismicity coming up, and the buildings are falling on that zone basically is to be evacuated, or at least they should be earmarked, and mitigation rehabilitation should be positioned in a nearby location, so that whenever it happens, we cannot make the building get destroyed or evacuate just like that, but at least we can position our measures. We can give our remedial, we can be prepared with a remedial measures in the nearby location. So that is all from my side. I thank you for carefully listening to this lecture, and in 5 minutes time from now I will be ready to take up questions. Thank you.